Welcome everybody once again. So we are in our third class for module 5. We are studying the analysis of curved beams. So in the previous classes, we saw analysis of a cantilever curved beam. We saw analysis of a cantilever curved beam which forms a quadrant of a circle. Okay, that formed a quadrant of a circle. We saw the cantilever beam with a concentrated load at the end, and the second problem we saw a cantilever beam curved in plan with UDL. So these problems we saw in our part 1 and part 2. Now today we will see analysis of a semicircular curved beam. So the question is, your figure shows a curved beam semicircular in plan. So you can see a curved beam. So this is a semicircular in plan and supported on 3 equally spaced supports. So you have 3 supports, support A, support B and support C. So these 3 supports, these are hinged supports and these 3 supports are equally spaced. The beam carries a UDL of W per unit of the circular length. Analyze the beam and sketch the bending moment and the twisting moment diagrams. So this beam carries a UDL. Okay, this curved beam, over its curved length, it carries a UDL of W per unit length. Okay, so we have a hinge at A, another hinge at B and another hinge at C. So we have 3 hinges. So we know this beam, this curved beam is said to be statically determinate. Okay, because we have 3 equations. Sigma mx is equal to 0. This is a 3-dimensional structure. And we have sigma mx is equal to 0, sigma my equal to 0 and sigma mz equal to 0. Sorry, sigma fz is equal to 0. And hence, we have 3 unknowns. A vertical reaction at A, vertical reaction at B and vertical reaction at C. So 3 unknowns, 3 equilibrium equations, which means our beam is statically determinate. Okay, now we need to find the vertical support reactions. So step 1, we will find the vertical support reactions. So we have 3 reactions at A, VA, we will have reaction at B, it is VB, and reaction at C, it is VC. Okay, now what is the total load on the beam ABC? It is W per unit length. So this, if you take this as the center point O, OA is the radius R, OC is the radius R. Right? This OB is also of radius R. Now, this total length will be equal to, this ABC will be equal to, see this angle is pi, right? 180 degree, so it is pi. So this perimeter ABC will be equal to pi R. So R, radius into the angle subtended by this curve. Okay, we know if there is a curve like this, if this is R, this is theta, this length will be equal to R into theta, radius into theta, right? So this ABC will be equal to R into pi. Okay. So this distance is r into pi. Now, listen carefully. So the total load will be equal to W into the distance, that is the length, r into pi. So we will write total load on beam. Total load on beam A, B, C will be equal to the intensity of load is W. The total length of the beam is r pi. Okay, so W r pi. Now, see from the diagram itself you can understand that VA will be equal to VC. VA, this is a symmetric. It is subjected to UDL. So VA will be equal to VC. So vertical load VA is equal to VC. Now we will take the moments of all the forces about the point B. So you consider point B. So summation of all the moments about B is equal to 0. You can take either the left of B or the right of B. Okay. So taking the moments, we will take the left. So taking the moments to the left of B, sigma MB is equal to 0. So what we get is VA into perpendicular distance, that is R. It is clockwise, right? So we will take it as positive. VA into perpendicular distance towards B, that is the radius R. So clockwise we will take positive. So VA into R. Next, we have a load, this load up to AB. So what is the distance AB? See, it is like this, right? This is O, A, B. So this AB, if you draw a perpendicular line, this is 90 degree. So you have a W per unit length. So how much is this distance? AB is, OA is R, OB is R. So R into pi by 2. This is R into pi by 2. Right? So this distance AB is R into pi by 2, 90 degree. So R into the angle subtended by the chord, that is 90 degree. Right? So R into pi by 2. Now, what is the load? That is W. So we get W into R into pi by 2. So this is the load multiplied by the distance. How will you calculate the perpendicular distance? See, this is a semicircular arch, right? If you take a semicircular arch, listen. If you take a semicircular arch, the centroid will be equal to, see, if you take this point, the centroid will be equal to 2r by pi. This distance will be equal to, this is the centroid, and this distance will be equal to 2r by pi. This is 2r by pi. So totally it is r, right? So how much is this? This is b, right? So bg will be equal to r minus 2r by pi. So what you get is, see, your load, this total load will be acting like this. Sorry. Will be acting like this. That means this line of action of a force will pass through the center of gravity or centroid of the semicircle. If you take it as a quarter circle, this will pass through the center of gravity of the quarter circle. If you take the quarter circle also, see the centroid is the same. It is 2r by pi. So what you get is, this is your total load. That is WR into pi by 2 into, see this will pass through the centroid. So the perpendicular distance is BG. So what is BG? R minus 2R by pi. So it is clockwise or anti-clockwise towards B? This is anti-clockwise towards B. So we will take the negative value. So minus W R pi by 2 into R minus 2R by pi. So we get minus W R pi by 2 into R minus 2R by pi. So anything else? No. So now we have taken, see, we are taking moment about this point. B is equal to 0. We are considering the left of B. So VA into perpendicular distance R minus, because this is clockwise about B. When you take this load, it is anti-clockwise about B. So this load is W into R into pi by 2, this distance, multiplied by, when you are taking the point of application of this load, it will pass along the centroid. So that distance is equal to, so from here, this is the centroid G and this is 2R by pi. Okay, so this distance is R minus 2R by pi. So nothing else. So this VA is over, this load is over. So is equal to 0. Is equal to 0. So from this what we get is VA is equal to WR pi by 2 into this R, you can bring it to the side, R minus 2R by pi is equal to 0. You can cancel this R. So we get, and you can take 1 R out. So you get VA is equal to pi W by 2 into pi R minus 2R by pi is equal to 0. You can cancel this pi. You can take R out. So you get VA is equal to pi minus 2 into WR by 2. So VA is equal to VC. Right? So VA equal to VC equal to pi minus 2 by 2 WR. Okay. So now we know, we found out what is vertical reactions VA and VC. Now what is the vertical reaction at B? So VA, upward loads is equal to upward reactions is equal to downward loads. So VA plus VB plus VC is equal to this total load. Total load is W pi R. So from that you can find the VB. So total load is W pi R or WR pi, W into R pi. So we have VA plus VB plus VC. Total upward loads is upward reactions is equal to downward loads. So total downward load is W into pi R. So VB is equal to pi WR minus 2 times VA plus VC, right? So both are same. So 2 times pi minus 2 by 2 into WR. You can cancel this 2 too. So we get VB is equal to pi WR minus pi WR plus 2WR. So cancelling these both, we get VB is equal to 2WR. Okay, so our vertical reaction is over. Now so the first step is over. Step 1, vertical support reactions. We have determined the vertical support reactions. Now we will move on to our step 2. Step 2 is to find the bending moment. Okay. So step 2, we will find the bending moment. So for finding the bending moment, we will consider a section X at an angle theta from OA. So we will consider some section X at this point. Okay. So we'll draw here. Or else wait. I will move on to the next page. Okay. So step 2 is bending moment. So for finding the bending moment, we will consider a section X making an angle of theta with OA. So we will take this half, that is ABO. We will consider this portion ABO. So this is a B. This is A. And this is O. Now take a section X. Okay. Consider a section X. And if you extend this X will make an angle of theta with OA. So consider a section X located at an angle theta with OA. Now, see, because it is subjected to UDL, this section is subjected to a UDL load, right? So that in this in this portion from A to X, you consider a small stripe, okay? You consider a small stripe and this small stripe makes an angle of d pi. So this smaller stripe, you consider a smaller stripe, and this smaller stripe subtends an angle of d pi with O. And this angle can be taken as pi. This is pi and this is d pi. Okay, so take a small segment. So this segment, the length of this segment will be equal to, see, this is radius r, right? So this segment r of radius r and angle subtended is d pi. So this segment is r into d pi. So take a segment r into d pi at an angle pi from x. From x at an angle pi, you take a segment r into dx. Okay, now we can consider the bending moment at x. So how will we find the bending moment at x? So bending moment at x, that is m theta. So m theta is equal to, here we have a vertical load VA, right? So up to, see, this x, this section is making an angle theta with OA. So x is varying from 0 to 90 degree, right? This section x is varying from, or theta varies from 0 to 90 degree. 0 to 90 degree. So m theta is equal to the moment due to this load VA. VA is acting at a point A. So VA into perpendicular distance, right? So perpendicular distance about x. So what is the perpendicular distance about x? From this, see, from this point, we can draw a perpendicular towards OX, right? So this is sorry. See, from this you can draw a perpendicular. From A, you draw a perpendicular towards OX. So we will take this point as N. So m theta is equal to VA into perpendicular distance towards OX, that is AN. So it is clockwise, we will take it as positive. So we get VA multiplied by AN. Now see this load, this UDL varies from, UDL is from A to B, right? So theta varies from 0 to 90 degree. So it is anti-clockwise towards x. When you take towards x, it is anti-clockwise. So minus theta is varying from 0 to, finally we will take it from 0 to 90. Now up to x, that is bending moment at x. For bending moment at x, it is 0 to theta. So 0 to theta. Here, that is, for this segment, the load is W into, W is the intensity of load. For a distance, the segment is R into d pi. R into d pi. So load is over. Load into the perpendicular distance. So what is the perpendicular distance now? This point. So we will take this as n. We will take this as m. N. We will take this point as P. So perpendicular distance is PM into PM. Okay. Now find what is AN and what is PM. So we know you take triangle OAN. Okay. So taking the triangle OAN, we get sin theta is equal to AN by AO. So AO is the radius R. Therefore, AN is equal to R sin theta. So AN is R sin theta. So this AN is R sin theta. Now what is PM? See this, I have, in order to make you understand, I have taken it as, I have drawn it as a larger section. So actually this section, this segment makes an angle of pi with the x-axis. So we will take triangle OPM. OPM. This is a small segment. Okay. In order to differentiate, I have drawn it as a larger segment. Actually, it is very small segment. So you take triangle OPM. You get sin pi is equal to PM by see this OP. PM by OP. OP is the radius R. Therefore, we get PM is equal to R sin pi. So, we will substitute these values here. We get M theta is equal to VA into AN. So, what is AN? Sorry. VA, we will substitute the value. We have already found what is VA in the first step. So, VA is equal to pi minus 2 by 2 into WR. So, pi minus 2 by 2 into WR into AN. AN we have calculated as R sin theta. So, R into R sin theta minus integration of 0 to theta W this WD R into d pi. This is R, right? W into R into d pi. Okay. So, W R into d pi into what is PM? R sin pi. So, R sin pi. So, this is equal to M theta is equal to pi minus 2 by 2 into W R square sin theta minus integration of 0 to theta W R square. This R into R square sin pi into d pi. So this is equal to, so m theta is equal to pi minus 2 by 2 w r square sine theta minus, you can take this w r square constant outside. So w r square into integration of sine theta is minus cos theta, right? Integration of sine theta is minus cos theta. So it is minus cos pi 0 to theta. So this is equal to pi minus 2 by 2 w r square sine theta minus w r square into, so pi is replaced by theta. So minus cos theta. Minus cos theta minus of minus cos 0. Cos 0 is 1. So you get 1 minus cos theta here. So m theta is equal to, you can take w r square common outside. So w r square into pi minus 2 by 2 into sine theta minus 1 minus cos theta. Okay. So this is your expression for the bending moment at x for a semicircular curved beam. Okay. So remember this. So you should get this expression for the bending moment at a section x. So now look into the diagram. We have obtained bending moment at a section x. Now we need to find the variation. That is, what is the bending moment at A and what is the bending moment at B. Then only we will be able to draw the variation of bending moment. Okay. So now, what is the bending moment at A? So bending moment at A, we will take it as MA. So bending moment at A is MA is equal to. So at A, we know theta is equal to 0, right? What is that? See, at A, theta is equal to 0. At B, theta is equal to 90 degree. At A, theta is equal to 0. At B, theta is equal to 90 degree. So at A, we know theta is equal to 0. So bending moment at A, MA will be equal to W R square into sine 0 is 0 minus 1 minus, so 0 minus 1 minus cos 0 is 1. So you get 0. So 0 into any number is 0, you get 0. So bending moment at A is 0. Now what is the bending moment at B? So at B we know theta is equal to pi by 2. Theta is 90 degree. So our bending moment at B will be equal to W R square into pi minus 2 by 2 sine 90 degree is 1 minus 1 minus cos 90 degree is 0. So MB is equal to WR square into pi minus 2 by 2 minus 1. So we get minus 0.429 WR square. So MB is equal to minus 0.429 WR square. So it is minus, right? Minus means your bending moment is hogging moment. So you will write here your bending moment is hogging. It is minus, so bending moment is hogging. Either write hogging or give minus sign. It should be very clear. Okay. So now we will draw the variation of bending moment. So we know bending moment at X, bending moment at A is 0, bending moment at B is hogging. So how can we draw the bending moment diagram? Okay, we will draw the bending moment diagram here. So, okay, we'll draw it here. So this is A. So this is our semicircle, right? Okay. So this is C and this is B. So we found at A bending moment is 0, at B bending moment is minus 0.429 hogging. See, how will we draw the sagging bending moment? It will be like this. If the bending moment is positive, your deflection is like this, right? Your deflection is like this. You will draw the bending moment like this. If it is positive, this means the deflection is sagging. If the deflection is hogging, you will have the deflection like this. You will have the deflection like this. This is hogging and your bending moment will be negative. You will be drawing the bending moment below, right? Bottom. So remember this. Similarly, we will draw here. If it is hogging, your bending moment comes below. So when you take AB, for AB, see this point, okay. So now at A, your bending moment is 0. At B, your bending moment is a hogging bending moment and it is the value is 0.429 WR. Okay, so it comes below. It is negative, so it is coming below your plan, right? So from here, your bending moment will be like this. Okay, so this is your bending moment diagram. So actually it will be okay. Okay. So this is your variation of bending moment diagram from A to B. So similarly, you will have from B to C also. So that means, see, we have analyzed only for one half because it is a symmetric. We will proceed it for the other half also. So for the other half, that is for BC, your bending moment will be like this. At C, your bending moment will be 0. At B, your bending moment is hogging, that is minus 0.429 WR. This is too big. Okay. Hope you understood. Okay, this is the variation of bending moment diagram. So now you need to find two more things for bending moment. One is, see what is the maximum bending moment. So here you have the maximum bending moment, right? So what is this value? What is the value for maximum bending moment? And what is, at what point the point of contraflexure acts? So this point is called, that is the bending moment changes from positive to negative. This is positive, this is negative. Here it is positive and this is negative. So you have to find maximum bending moment, and at what point the bending moment is changes its sign from positive to negative. That is the point of contraflexure. You have to find these two things also. Okay, so how can we find this? So first of all, we will find the maximum bending moment. So before that, for drawing the maximum bending moment, so this is our point O. So we will join these lines to O. See, from maximum, this is O. So from maximum, you join this to O. From this point of contraflexure, you draw a line to O. From B, you draw a line to O. So similarly, from this side also. Okay. So now we need to find this. This is our M max. Maximum bending moment, and this is the point of contraflexure. That is, your bending moment changes from positive to negative. Positive and negative. So here negative and positive. Okay, now our aim is to find the angles. What is this angle and what is this angle? If you have found these two things, your problem is over. Over for bending moment. Then similarly we have for twisting moment also. Okay, now we will find the maximum bending moment, right? Okay, so how will we find the maximum bending moment? It occurs some point between A and B. Okay, this maximum bending moment is occurring at some point between A and B, and also between B and C, because it is symmetrical. So for MB to be maximum, so M theta to be maximum, the condition is, we know for finding the maximum or minimum, the differentiation will be equal to 0. So for finding the maximum bending moment, dm theta, so bending moment, differentiation of bending moment with respect to theta will be equal to 0. This theta is varying from 0 to 90 degree. Theta is varying from 0 to 90 degree. So bending moment, differentiation of bending moment is equal to 0. So what is bending moment? This is m theta, right? So differentiation of this m theta is equal to 0. So we will write differentiation of this equal to 0. This m theta is equal to 0. We will replace m theta by WR square into pi minus 2 by 2 sin theta minus 1 minus cos theta. So we get d by d theta of, so m theta is WR square into pi minus 2 by 2 sin theta minus 1 minus cos theta is equal to 0. So when you differentiate this is equal to 0, see this WR square is constant. WR square is constant. So we get d by d theta of, you can take W r square out, and when you bring it, okay, nothing, okay. Okay, W r square is constant. So W r square into differentiation of pi by 2 by 2 sine theta. Pi minus 2 by 2 is constant. Differentiation of sine theta is cos theta. So cos theta minus differentiation of 1, differentiation of constant is 0, minus differentiation of cos theta is minus sine theta. So minus into minus plus sine theta is equal to 0. So W r square is equal to 0, or this term is equal to 0. We need theta, right? So we will take this term is equal to 0. So pi minus 2 by 2 cos theta minus sine theta is equal to 0. So we get pi minus 2 by 2 cos theta is equal to sine theta. So we get sine theta by cos theta is equal to pi minus 2 by 2, from which we get tan theta is equal to pi minus 2 by 2. Therefore, we get theta is equal to 29 degree 43 minutes. So you will get a maximum bending moment at theta is equal to 29 degree 43 minutes. So this angle, see, maximum bending moment is this line. So this angle is 29 degree 43 minutes. Now we will substitute 29 degree 43 minutes in m theta to find m max. Okay. So m max substitute. So we get m max is equal to m theta at theta is equal to 29 degree 43 minutes. So we know this is m theta, right? This is m theta. W r square into pi minus 2 by 2 sine theta minus 1 minus cos theta. So we get m max is equal to W r square into pi minus 2 by 2 sine theta. Theta is 29 degree 43 minutes minus 1 minus cos 29 degree 43 minutes. So we get m max is equal to W r square into 0.2830 minus 0.1315. So m max is equal to 0.1515 W r square. It is positive. That means it is sagging. Positive means sagging, right? So what is the value? It is plus 0.1515 W r square. So we will mark it here. So maximum value m max is equal to 0.1515 W r square. So this is the maximum value. So m max is over. We have found the angle, we have found the intensity also, magnitude also. Now we will find what is the point of contraflexion. Okay. So what is the point of contraflexion? How will we find the point of contraflexion? Point of contraflexion is the point where the bending moment changes its sign from positive to negative. So at this point, bending moment is equal to 0. So we will find the angle theta for which the bending moment is equal to 0. So now we are going to find the point of contraflexion. Okay. So we are going to find the point of contrafluxure. So for finding the point of contrafluxure, bending moment m theta will be equal to 0. So what is m theta? W r square into pi minus 2 by 2 sin theta minus 1 minus cos theta will be equal to 0. So we get W r square into pi minus 2 by 2 sin theta minus 1 minus cos theta is equal to 0. Okay, so again W r square is equal to 0 or pi minus 2 by 2 sin theta minus 1 minus cos theta is equal to 0. So pi minus 2 by 2, we need to find theta. So pi minus 2 by 2 sin theta minus 1 minus cos theta is equal to 0. So we get pi minus 2 by 2 sin theta is equal to 1 minus cos theta. Now sin theta by 1 minus cos theta is equal to 2 by pi minus 2. You can take it in the other way also. 1 minus cos theta by sin theta is equal to pi minus 2 by 2. Now it is hard to find what is theta. So what we can do is we can use trial and error method. Okay, you substitute the value for theta. See, you can see from the diagram, your theta lies between 90 degree and 29.43. It is greater than 29.43. It is less than 90 degree. Right? See this angle. You need to find what is this angle. So this angle is greater than 29 degree 43 minutes and it is less than 90 degree. So you put the values, intermediate values. First of all, you put 30 degree, 40 degree, 50 degree, 60 degree and at one point you will get theta is equal to 0. So here for this case, theta will be 0. Theta, that is this bending moment, will be equal to 0 when theta is equal to 59 degree 27 minutes. This is obtained by trial and error method. Okay, trial and error method. Substitute the value for pi. Then you substitute different values of theta. So it is 59 degree 27 minutes. Right? So here the point of contrafluxure. Where is that? Okay. So the point of contrafluxure occur at an angle of 59 degree 27 minutes. So how can you conclude this? You can conclude the point of contrafluxure occurs at 59 degree 27 minutes from OA. And this is our bending moment diagram. So our completed bending moment diagram is this. Okay. Now we will one more step to complete. Like bending moment, we have to find the twisting moment. That is our step 3. So twisting moment, we will find what is twisting moment t theta. Then we will find the variation of the twisting moment. Then the angle where the maximum twisting moment occurs. What is the maximum twisting moment? And what is the point of contrafluxure for twisting moment? Okay, so that is our step 3. We will move on to step 3. Okay, so step 3 is twisting moment. See, for twisting moment, It is similar to the bending moment. See, previous two cases we saw, right? Now listen. See, this is bending moment. Bending moment at x is VA into AN. VA into AN, right? Whereas twisting moment is VA into XN. That is the distance perpendicular to this AN with respect to XN. So for twisting moment, it is VA into XN minus 0 to theta WR into R pi into, see, for bending moment, the distance is PM, right? For bending moment, the distance is PM. For twisting moment, the distance is XM, this distance. That is the only difference. So what is AN is R sin theta. What is XN? XN is, see, for finding XN, you find ON first. So take triangle AOAN. So OAN is R cos theta. Sorry, OAN. ON is R cos theta, right? R cos theta. So XN is R minus R cos theta. Okay, we will find it anyway. See, taking the same triangle OAN, already we have taken from OAN what is sin theta, right? Now you can find what is cos theta. You put cos theta is equal to ON by OA. So cos theta, see, same triangle. You take triangle OAN, triangle OAN, triangle OAN, cos theta is equal to ON by AO. So ON is equal to R cos theta because AO is the radius R. Now ON is R cos theta. We need XN. So what is XN? R minus R cos theta, right? So XN is equal to R minus R cos theta. So XN is equal to R minus R cos theta. Now for this UDL, it is XM. You need to find XM. So now you will take triangle OPM. Again OPM, this triangle. See what you have taken already, OPM. If you take triangle OPM, your cos pi will be equal to OM by OP. OM by OP. So you get OM is equal to R cos pi. OM is R cos pi. So what is XM? R minus R cos pi. So XM is equal to R minus R cos pi. These two things are what is needed for twisting moment. So twisting moment is equal to VA multiplied by XN minus W into R d pi multiplied by XM. Okay. So step 5, twisting moment. Twisting moment T theta will be equal to VA into, instead of AN we have XN. XN minus integration of 0 to theta WR into R pi multiplied by, instead of PM we have XM into XM. Okay. So what we get is T theta is equal to VA. So VA we have already calculated. VA is pi minus 2 by 2 WR into what is xn? R minus r cos theta. Xn is r minus r cos theta. R minus r cos theta minus integration of 0 to theta WR into d pi into xm. xm is r minus r cos pi. R minus r cos pi. So we get this is equal to pi minus 2 by 2 WR square. You can take one R out. So WR square into 1 minus cos theta see, sorry, one mistake. See, when you take WA into the perpendicular distances xn, right? Where is xn? Xn. So when you take the perpendicular distance, it is anti-clockwise. Okay, anti-clockwise. The distance is this. This is the perpendicular distance, right? So this becomes minus and this becomes plus. So here this is minus and this is plus. Here it is minus and this is plus. So minus pi minus 2, pi minus 2. So plus, you can take this r out. So you get WR square into integral 0 to theta 1 minus cos pi into d pi. So you get minus pi minus 2 by 2 WR square into 1 minus cos theta plus WR square into integration of 1 into d pi, it is pi minus integration of cos theta is sin theta. So sin pi 0 to theta. So we get minus pi minus 2 by 2 WR square into 1 minus cos theta plus WR square into substituting pi by theta minus 0 minus sin theta minus of minus sin theta. Sin 0 is 0. So that is all. So we can take WR square out. So we get T theta is equal to, WR square multiplied by minus of pi minus 2 by 2 into 1 minus cos theta plus theta minus sin theta. So this is the twisting moment or the torsional moment at section X. Now we will find the variation of twisting moment, right? So variation of twisting moment. So variation of twisting moment at A, theta is equal to 0. Therefore, twisting moment at A will be equal to W R square into minus of pi minus 2 by 2 into 1 minus cos 0 is 0. Sorry, cos 0 is 1. So 1 minus 1 we get 0 here. So this term becomes 0 plus theta is equal to 0 minus sin 0 is 0. So twisting moment at A will be equal to 0. Twisting moment at B will be equal to twisting moment at B will be equal to, that is at B theta is equal to 90 degree. So pi by 2, theta is equal to pi by 2. So we get WR square into minus pi minus 2 by 2 into 1 minus cos 90 is 0 plus pi by 2 minus sin pi by 2 is 1. So we get this is minus pi by 2 plus 1. So minus pi by 2 plus pi by 2 gets cancelled, plus 1 minus 1 get cancelled, is equal to 0. So TA is equal to 0 and TB equal to 0. So our twisting moment diagram will be like this. This is A, B, C. So our twisting moment diagram is from A to B, from A0 to B0, some from B to C, from 0 to 0. It will be like this. Okay. So now we need to find, we will extend this. This is O. We need to find what is the maximum twisting moment. Okay. So we need to find what is this angle. So this is the maximum twisting moment. So T max, you need to find what is T max and at what angle. There is no need of point of counterflexion because at B it is a 0. It is always, we will see that negative or positive we will see. Okay. So how will we find the maximum bending moment? As we did in the bending moment, for the maximum twisting moment we take, so for maximum twisting moment we will take the differentiation with respect to theta is equal to 0. So d t theta by d theta is equal to 0. So we get d by d theta of t theta is w r square into minus pi minus 2 by 2 into 1 minus cos theta plus theta minus sin theta is equal to 0. So we get WR square into, this is constant, d by d theta of minus pi minus 2 by 2 into 1 minus cos theta plus theta minus sin theta is equal to 0. So WR square is equal to 0. We need theta. So differentiating this we get. So minus pi by 2, that is constant, right? Minus pi minus 2 by 2 is constant into differentiation of 1 is 0. Differentiation of cos theta is minus sin theta. So minus of minus sin theta, we get sin theta. Plus differentiation of theta with respect to theta is 1 minus differentiation of sin theta is cos theta is equal to 0. So we get 1 minus cos theta is equal to, we take this together, right? 1 minus cos theta is equal to pi minus 2 by 2 sin theta. So we get 1 minus cos theta by sin theta is equal to pi minus 2 by 2. So you can use trial and error method. So using trial and error method, we get theta is equal to 59 degree 27 seconds. So same as that for bending moment. Okay. So theta is 59 degree 27 seconds. We have the maximum twisting moment. So now we need to find the maximum value for twisting moment, right? So for finding the maximum value of twisting moment, we will put theta is equal to 59.27 degree in our twisting moment equation. So we get, now we are going to find the maximum twisting moment. So for maximum twisting moment, we know T theta is equal to WR square into minus pi minus 2 by 2 into 1 minus cos theta plus theta minus sin theta. So theta is equal to 59 degree 27 minutes. So we get T theta is equal to WR square into minus pi minus 2 by 2 into 1 minus cos 59 degree 27 minutes plus 59 degree 27 minutes See, when you are substituting theta here, you have to convert it into radians. So multiply it by pi into 180 minus sine 59 degree 27 minutes. So we get T theta is equal to, or T maximum, right? This is T maximum. So T maximum is equal to minus 0.1043 WR square. So in our twisting moment diagram, so this is negative and this is negative. So it is observed that the twisting moment is maximum at a section where the bending moment is 0. See, what is 59 degree 27 minutes? You can see in the bending moment diagram, at 59 degree 27 minutes, our bending moment is 0. Bending moment is 0. So, when your bending moment is 0, you have the maximum twisting moment. So, you can conclude that it is observed that the twisting moment is maximum at the section where the bending moment is 0. So that's all for today. Thank you. Thank you for listening. We will see one more. There is one more problem that we will see in the next class. So it is, see, if you understand the concept, it is very simple. Just finding the vertical reactions, then bending moment, maximum bending moment, point of counterflexion, twisting moment, and maximum twisting moment. Thank you.